Hi, welcome to video 9.6a, the ratio test and the root test. These are the last two tests for series of constant terms, and then we'll be moving on to series with variable terms, which will be called power series. And the ratio test we will use constantly with power series. So the ratio test is a very important one for power series. Okay, so here's our list, which we keep adding to. Nth term, geometric, integral test, p-series, direct comparison, limit comparison, alternating series, and now we're going to add ratio and root test. They're actually quite simple tests. Okay, so these are the last two tests for convergence of series of constant terms. The ratio test says let the summation un be a series with non-zero terms. So these can have negative terms. It can be all positive terms, all negative terms, alternating. You can have 3 positives followed by 5 negatives followed by 7 positives. It doesn't matter. The only thing matters is that you have non-zero terms. So now, of course, if your first term is 0, that's not a biggie because you can just disregard that. But you can't have like 3 non-zero terms and then a 0 term. They all have to be non-zero terms. Okay, so here's what happens. You don't have to compare it to anything. You simply find the limit as n goes to infinity of the absolute value. So that'll take care of, like, if there's an alternating series, you'll just ignore the -1 to the whatever, of un plus 1 over un. So it's really the n plus first term of your u over the nth term. If, now you can see the 3 situations, if that limit is less than 1, then the series un is absolutely convergent, therefore is convergent. If it's bigger than 1, it's divergent. If it equals 1, unfortunately, that means there's no conclusion, and you will have to try another test. Okay, and here it is easy, less than, convergent, greater than, divergent, that kind of makes sense. But remember, if it's equal to 1, there is no conclusion. Okay, so in numbers 13 through 34, if you just look at these questions, it says use the ratio test to determine the convergence or divergence of the series. Now, I can tell you right now that the ratio test works very well when you have factorials in your UN. Okay, so for example here, and you'll notice I'm going to guess that a lot of the questions have factorials. Notice number 14, 15, 16, 23, 27, 28, 30 all have factorials in them. So that's very common with the ratio test. Okay, so you have to make sure they're all non-zero terms. Just write out the first 2 terms. It's very easy to convince yourself that's the fact. Ratio test means you got to find the limit as n goes to infinity of un plus 1 over un. So un plus 1 will be 3 to the n plus 1 over n plus 1 factorial. Now you're going to be dividing by un, which of course means you're going to be multiplying by the reciprocal. So I'm usually going to skip this step and go right to un plus 1 instead of over the un. If it's a fraction, simply multiply by the reciprocal of that fraction. Now, the reason it works so well with factorials, of course, if you remember, when you have factorials like this and they're being multiplied, you can simplify. So you take the larger one, n plus 1 times n factorial. That'll cancel with the n factorial. This is 3 to the n plus 1 over 3 to the n, which will end up being 3 to the 1. So you end up with 3 over n plus 1, and of course the limit at infinity of that is 0. Now remember we said if you get an answer less than 1, you can't say because it's 0. That's not the theorem. The theorem says if that limit is less than 1. So since that limit is less than 1, the ratio test, the series is absolutely convergent and therefore convergent. Here's number 24. So this is an alternating series. You can see that these are all non-zero terms. When we go to do the ratio test, the absolute value is simply going to make this disappear. I'll still have these guys right here. So it's un plus 1, which is 3 halves to the n plus 1 over n plus 1 squared, divided by un, which is times the reciprocal of that expression. Again, you have 3 halves to the n plus 1 over n. Take the top exponent minus the bottom exponent. You're left with 3 halves to the 1. This is n squared over, if you expanded, n squared plus 2n plus 1. So really, this is 3n squared over 2 times that denominator. Degree of the top equals degree of the bottom. Limit at infinity is leading coefficient over leading coefficient. So again, because that limit is greater than 1 by the ratio test, the series in this case diverges, right? This is like number 31. Again, you'll make sure they're all non-zero terms. You'll find the limit is the absolute value of un plus 1 over un. These are all positive terms anyway, so the absolute values are redundant. Un plus 1 is 4 to the n plus 1 over 3 to the n plus 1 plus 1. So here's that. Divided by un means divided by this expression, so I'm turning that to multiply by the reciprocal. Again, 4 to the n plus 1 over 4 to the n. You'll take n plus 1 minus n. You'll be left with 4 to the 1. And then you have 3 to the n plus 1 over 3 to the n plus 1 plus 1. So I can pull that 4 on the outside, and if you plug in infinity, this will give you infinity over infinity, which gives you the right to use L'Hopital's. The derivative of 3 to the n is 3 to the n times ln 3. The derivative of 3 to the n plus 1 is 3 to the n plus 1 times ln 3 plus 0. The ln 3's cancel. This simplifies down into 1/3, and of course the limit as n goes to infinity of 1/3 is just 1/3, and you got times 4. It's equal to 4/3. Since it's bigger than 1, by the ratio test, the series diverges. The root test, it's used, one of the times it's used is when you have n's in the exponent and it's not a geometric series. So it's called the root test because you're going to find the limit as n goes to infinity of the nth root of the absolute value of un. Interesting things, same exact conclusions. If that limit is less than 1, then your series is absolutely convergent, therefore convergent. If it's greater than 1, it's divergent. If it equals 1, no conclusion, and you'd have to try. So here's an example. See with the n and the exponent. Again, write out the first few terms. Somehow I don't have that -1. Oh, but it's the ANs that have to be positive. They just have to be non-zero, so negative or positive doesn't matter. Okay, now, it turns out, of course, if you rewrite this, this is -1 to the 3n times 3n to the 3n over 2n plus 1 to the 3n. So in effect, it actually is an alternating series. But they have asked you in these questions, I think at number 42, it actually says use the root test, okay? So the root test says as long as these are all non-zero terms, which they are, find the limit as n goes to infinity of the nth root of the absolute value of an. So the absolute value will make this -1 to a power disappear, and you'll be left with this expression here. Now, both of them are to the 3n, so I can raise them all to the 3n. And then, of course, I can simplify this radical. If you take this exponent and divide it by that exponent, it ends up being cubed. Or you can look at it as to the power of 3n over n, still gives you cubed. You have the limit of the cube of a function. Well, that's equal to the cube of the limit of the function. The limit of this function is 3/2. 3/2 cubed is 27/4. And again, since the limit is greater than 1, the series diverges.